Portugal. His name is Pedro Teles, and he will close the session with yet another application of the Penelope Monte Carlo code. So we have focused in this session on applications of two main Monte Carlo codes in radiation dosimetry. There are a few more. One may argue that there are other codes existing, including, for example, Mcmp, that is still a valuable code in radiation dosimetry, or, for example, Giant, who has some tools to extend the calculations from high energy physics, for which it was originally conceived, down to the low energy range. However, given the scope of use of Penelope and Aes Nrc in fundamental questions in radiation dosimetry and its application in the domain of medical physics, as well as the development of primary standards, correction factors, and so on, we have decided to focus in this session on these two codes, Penelope and Aes Nrc. So while we wait for the plenary speaker to arrive, Ernesto Mainegra, I can see on the monitor two of the speakers in this session. One is Jorge Borbinha. George, test your microphone, please, for a moment. Just turn it on.
Yes, hello.
Okay, that's good. Thanks for coming. And another one I can see here is Grichar Valdes Santurio from Denmark. Grichar, say hi.
Hi. Can you hear me?
Okay, we can hear well.
Super.
Okay, great. So we're waiting for Ernesto to come. So as I mentioned, Ernesto Mainegra is speaking from NRC, from Canada, and his institute has been maintaining and developing the Aes code for, I wouldn't want to be wrong here, but I think for the last 20 years or so. Maybe not necessarily Ernesto directly for 20 years, but he's been involved in the development of several aspects of the code. And Ernesto will give a talk that covers the range of applications that are built in the Aes Nrc code. And as we speak, I can see another speaker coming in the meeting. Here he is. His name is Pedro Peixoto Teles. Pedro, I just wanted to check your microphone. Can you just turn it on so you can say hi to the audience?
Hello.
Good. Good. Thanks for joining in. So at the moment we're only missing Ernesto, and I was just introducing to the audience that we have 4 speakers. What you see here, other than me, that I'm not speaking at all, is the 3 speakers that will follow Ernesto's talk. And like I mentioned earlier, Ernesto's talk is going to be lasting for approximately 40 minutes, after which we will have Grichar Valdes Santurio speaking about one application of Aes Nrc, and then we switch to the Penelope applications, one from Jorge Borbinha, one from Pedro Teles. But all questions should be please addressed at the end, so please do not rush in with the questions, or actually don't expect questions to be addressed at the end of each talk. We will have a final panel with all questions. As far as I understand, all questions will be received by text, and then I will be reading them. And of course, if you feel that you want to write a question in Portuguese, I will do my best to read it anyway, even if I'm not a native speaker or my understanding is limited. So while we wait for Ernesto to join, I just wanted to ask Guilherme if I was correct. So are questions to be received only at the very end, or
No, you can receive for all the section, and then at the end will be answered all the question.
Okay, so but answers to the questions are not going to be provided at the end of each talk. So the speaker should be holding, okay? Holding,
yes.
Okay.
That's and at the end, if the person asks, you put everything this question at the end.
Mm-hmm. Okay, so we are only missing Ernesto. That happens to be the first speaker. So has anyone of the speakers, I mean, has got his cell phone or can text him a message? I don't have a cell phone for Ernesto, just to make sure he's around, but I'm sure he should be arriving in a moment or two. Grichar, I know you know Ernesto well. Do you have his mobile phone by chance?
I'm writing him now.
Okay, good. Thank you.
But that doesn't mean that he will see it. So.
Well, just try, yeah, because I don't have his cell phone. I have his email, but his email might be not be the best way to contact him. And he has not written to me in the meantime. I'm sure his time zone was correct because we tested last couple of days ago. So he should be not making any mistake in terms of time zone.
Here, right, for the test, the first of the overall.
Yeah, and I can see there are 85 participants. Thank you for joining in. That's a nice session. I cannot see from how far are you participating, but I understand that this conference is being broadcasted and received everywhere. I'm speaking from Europe, from Rome, and we actually, 3 of 4 speakers are Europe, and 1 is in Canada in this session.
And you mentioned that in Brazil now is our lunchtime.
Yeah, because it's 12 o'clock.
Yes.
Have you foreseen any interruptions during these sessions, Guilherme?
No, nothing. I put every section interrupted, and then you can choose what you want, but don't stop to lunchtime or everywhere.
So I think I would wait for another few minutes, and then if Ernesto doesn't join in, I would be...
I just tested him, and then he replied, like, what? I thought it was a different time, so I don't know if he will like quickly run to the computer.
Okay, so why don't we do this way? Because we're already, say, 10 minutes in. If you would be happy, Grichar, would you be happy to start with an application of EGS?
Yeah, I could start.
Yeah, and then after, because I wouldn't want to waste too much time in if Ernesto has to arrive. Unless he said he's really ready to come in. Oh, okay, here he's coming. Hold on, Grichar.
Yeah.
He might be coming in. Here he is. Ernesto, you should turn the microphone on, please.
Hello.
Excellent. Okay. Thanks for joining. We were just about to have to start without you, I'm afraid, but no, you're here. I'm happy that you are. So I
understood. I thought it was 11 because it was Sao Paulo time.
No, I think it was 12. But anyway, don't worry. It's good that you're here. And I already have in the last few minutes I just mentioned who are the speakers, and I also mentioned who are going to be, what are they going to be talking about, and I introduced you as our plenary speaker, making an overview of the Aes Nrc code system. So after you, Ernesto, we will have Grichar delivering a specific talk on one potential and possible application of EGS in a dosimetric problem. And then we switch to the Penelope applications with Jorge and Pedro. So I think without any further hesitation, I would pass it on to you so that you can project your presentation on the screen and start. And I will count 40 minutes from now. And all your questions, Ernesto, we will receive them throughout, but then we will be addressing them in the end, in a final session. So please stay on, and then we'll go on with questions to your talk. So whenever you're ready.
All right. Right. Good afternoon, dear friends in Brazil. I hope we're all staying safe and healthy in these uncertain times. In this presentation, I want to tell you a small story on how the Monte Carlo method become an acceptable tool in radiation dosimetry, while at the same time, I want to showcase some of the Aes Nrc applications that we use here in the NRC, and I found very useful, and I hope that could be of utility to all of you. I'm finalizing with a few words on how you would go about validating your own application when you want to be able to offer credible results. So Monte Carlo is actually a place in the south of France, along the French Riviera. And it's actually a very small neighborhood in the Principality of Monaco, and it's very well known for its gambling casino. And it is probably because of that that the method was named Monte Carlo. But when we talk about Monte Carlo, we think use of random numbers. But actually, a much better definition is to say we're using random numbers to solve an integral numerically. And as a numerical method, Monte Carlo is mathematically sound. It's robust and stable, and its uncertainty is inversely proportional to the square root of the sample size. And this integration method is actually more efficient than any other integration method over 3 dimensions. So for a Monte Carlo simulation where we have 6 dimensions per particle, using Monte Carlo is the most efficient way of tackling this problem. And this constant complexity of Monte Carlo makes it ideal for tackling very complex situations. So many people in our field in radiation dosimetry know or have ever heard of a Monte Carlo simulation code. So I'm listing a few here. So we have Aes Nrc and Penelope as codes that allow you simulating the transport of photons, electrons, and positrons. But then we have another group of Monte Carlo codes such as Fluka, Jean4, and Mcmp that would allow you the simulation of many particles. So by my expertise or experience is using Aes Nrc. Aes stands for electron gamma shower, the NRC version. And it's a general purpose Monte Carlo code that allows you simulating the transport of particles between 1 keV and several GeVs. It has been coded for efficient sampling, so it's a very fast Monte Carlo code, and it's also very accurate. It has been shown that it can produce accurate results at the 0.1% level when modeling ionization chambers. And because of this, it's seen as the gold standard for electron photon transport in radiation and dosimetry. So, but in the beginnings there was no Monte Carlo in radiation dosimetry. It's only in the mid-80s, beginning of the 90s, when there was evidence brought forth that potentially one could use Monte Carlo accurately to produce certain corrections that were required in dosimetry. Then there was a flurry of activity in the 90s, bringing experimental validation to these calculations. And it was finally in the early 2000s that it was internationally recognized that Monte Carlo could be an accurate tool for producing corrections and basic dosimetric quantities. And I want to give the example of the wall correction story for cobalt-60 Erkmer standards. The cobalt-60 Erkmer standard at the NRC was developed around 1958 by Bill Henry. It was a cylindrical ion chamber, and many of the basic quantities that were required and corrections were either obtained from values in the literature or from a few measurements. But there were significant approximations and omissions, so certain corrections were assumed to be 1. However, the uncertainty quoted for the standard was 0.5%. The cobalt-60 Erkmer standard relies on cavity theory. So the assumption that is made is that the measuring device will not perturb the photon fluence as it irradiates the measuring device. And under these assumptions, you can connect the quantity Erkmer with a charge measurement by multiplying it with the mean energy to produce an ion pair per unit charge, divided by the mass of this cavity, which needs to be measured accurately, times the fraction of non-radiative energy depositions, so that you can get from collision kerma to total kerma. And then you need to also multiply by stopping power ratio and a mass energy absorption coefficient ratio. And that way you can go from a charge measurement to air karma. However, we know that there are perturbations when you introduce an ion chamber in a beam, in a photon beam. So we have corrections for the presence of the wall. We also have a correction that accounts for the non-homogeneity of some certain chamber compositions. We will also have to correct for contributions from the stem of our ion chamber. And we also correct for the divergence of the beam not being a parallel beam. So many of these perturbation corrections are very hard to measure, or originally were not possible to obtain with calculations. But one could do indirect measurements of the wall correction, for instance, using the so-called linear extrapolation to zero thickness. So you could do measurements of the ion chamber response for different wall thicknesses, and then plot the response as a function of the wall thickness and do an extrapolation, a linear extrapolation to zero thickness, and then assume that's your response without a wall perturbation. The stem correction, there was an ingenious method where you could put an extra dummy stem on top of the ion chamber, and then you could that way estimate the increase of the signal of an ion chamber from scattered from the stem. So there were methods and ways of trying to estimate these corrections experimentally. However, in the late 80s, beginning of the 90s, Alex Bielayev developed a nonlinear first order theory to calculate the wall correction. And he compared it to measurements done at NIST for 50 cc spherical chambers that were the standards at the time. And he found that there seemed to be a discrepancy as you move towards very small thicknesses of the wall. It seemed that his theory and the Monte Carlo calculations that he performed were different by 1% at zero thickness. So suggesting that perhaps the linear extrapolation to zero was underestimating this correction. However, because these chambers were really large, you can do actual experimental measurements on very thin walls. So you see the measurements that were available at the time, they were all in the linear regime. And these measurements were done for a cobalt-60 beam, but also for a cesium beam, because the cesium beam will have a very shallower buildup, very smaller buildup. So it was possible to use thinner walls past the buildup region, so that you could do more measurements at thinner walls. However, there was not at the time. There were no measurements in that nonlinear regime that could show this effect. So fast forward about 12 years later at the NRC, a smaller ion chamber, spherical ion chamber, was constructed that had very thin walls, and measurements were done by adding different hemispherical caps of different thicknesses. And measurements were possible in the nonlinear region, showing confirming Alex Bilayev's predictions that this region was actually nonlinear, providing evidence that potentially one should use the Monte Carlo corrections. And further evidence were brought forth then a year later, where another experiment was performed, whereby measurements were done with a cylindrical chamber that was our standard, the spherical chamber that was built the year before, but also a plane parallel chamber, the Mark IV. These three chambers were put in front of the cobalt-60 beam and corrected for wall perturbation using the correction extrapolated to zero thickness linearly, and their discrepancy was up to 2%. However, if you would use the Monte Carlo calculated a wall correction for these specific chambers, then the agreement was better than 0.3%. Another neat experiment that was part of the study was the measurement of the response of the plane parallel chamber, as it was shown here on the right, as it was rotated around the stem axis for different angles. And you can see in the graph in the middle how the response was decreasing with angle as the photon beam would see less of the cavity and would hit more of the structure of the wall. And then this curve showed this structure, this little shoulder close to 90 degrees. The measurements and the calculations using Monte Carlo simulations were in very good agreement. So the agreement was better than 0.3%. So this confirmed that EGS NRC could model the response of this ion chamber accurately. And also, if you apply the wall corrections calculated with EGS NRC, you would recover the response of the ion chamber at 0 degrees. So this was a good experimental evidence that the Monte Carlo simulations were accurate. And encouraged by all these results, the NRC Cobalt-60 air Kerma standard was updated in 2003, where many of the quantities that were required were obtained using applications from the EGS NRC code. So to obtain the radiative loss fraction G bar for air, a little code called G was used. And then for obtaining the mass energy absorption coefficient ratios, the application DOSRZ NRC was used. And for swapping power ratios, the code SPRRZ NRC was used. Then recently in 2019, I've redone the calculations to update the standard according to the recommendations of the RCRU report 90. But this time I've used the G code for calculating G bar, but also the mu-n overall ratios. And all the corrections that were required have also been obtained using Monte Carlo simulation. In 2003, the code CAVRZ NRC was used, which was tailored for modeling ion chambers in cylindrical symmetric geometries. And in the recent last year, I used the code cavity to be able to add more detail to the chamber model when calculating these corrections. So there's a lot of Monte Carlo calculated quantities that go into our primary standard for Cobalt-60. So I mentioned the G application. And this is a not very well known code that we distribute with EGS NRC. This is an application that will allow you to calculate the radiative loss fraction G bar for photon beams, or the radiative yield Y for electron sources. And the way these calculations are done is you start with your initial particle at the origin of an infinite phantom. And after that initial interaction, you follow the whole electromagnetic shower and classify the energy deposition events into radiative and non-radiative events. And that allows you to obtain these quantities. And this code can be used for monoenergetic and also spectral sources. It's not very well known, the code, because there was not a documentation until this year that I found the time to create a detailed documentation for the code. But since this application is already doing this classification of radiative and non-radiative energy depositions, we can also compute mass energy absorption and transfer coefficients when we're running this simulation. So we also output these two quantities when you do a simulation with the G code. Moreover, you can use the simulation in a photon-only mode, a photon source-only mode, where you can have only a source of photons, and then you can calculate the mass energy absorption coefficient very fast by using certain tricks. And this is the calculation type that I usually use with this code to generate all the large databases of mu-en values that are distributed with EGS NRC codes, such as cavity, XFAC, XConvMct, and XKerma, that require the calculation of Kerma. And once you are producing these absorption coefficients, then you can also compute Kerma from them, because the mass energy absorption and transfer coefficients are nothing but Kerma per energy fluence. So you can also output the Kerma per unit fluence in these calculations. So this is something that you can also calculate with the G code. And this is the only code that will calculate Kerma according to the exact definition of karma at a point. And this is very useful when you want to compare your own karma calculations, see how accurate they are. So there is a documentation that has been created with Doxygen. It will be soon put in our website for where we distribute the code on GitHub. You can have it in HTML format, but also I can provide a PDF if anyone is interested. And I will point out here, there's a section in the manual that will tell you what you need to do to generate large databases of energy coefficients, mass energy absorption coefficients, if you need it. There's a little script that is provided there that you can run on Linux to produce these databases. So officially in EGS NRC, there's 2 applications that are written for calculating karma. So we saw now the G code that will give you total and collision karma in an infinite phantom. But there's also the application Dosimetry NRC, which can also calculate karma, but only total karma, and for concentrically cylindric geometries. So other than that, you cannot use it, but it can cover a lot of situations. There's also a hidden option in the application cavity, which was usually originally designed for modern ion chambers. But because it was the first C++ application that we developed with the inclusion of the X++ library, it was a test bed for different options. So we can use cavity in photon calculation mode, and you can compute the fluence and the karma at a circular field anywhere in space, on a circular field that is defined by a point and a direction vector. So you could have a simulation, a beam simulation of an X-ray tube over LINAC, and then you can connect, you can use that as a source to cavity, and you can compute spectra very efficiently. And the reason why I'm mentioning this here is because I see in many publications or many works that people tend to use beam to model their LINACs or their X-ray tubes, and then compute huge, large first space files from where then you can extract a spectrum. But these tend to be very inefficient and cumbersome to deal with these very large files. If you use proper variance reduction techniques, you can obtain spectra with this application very efficiently. So a few years back, a colleague of mine requested that I tell him which application he could use for calculating karma, air karma, in a water sphere, 5 centimeter radius water sphere, irradiated by a liquid source contained in a glass vial. He also needed to remove the effect of scatter of the walls, the ceilings, and the floor. And considering the geometrical limitations of the codes on the right here, concluded that these codes were not the proper ones to do these calculations. So we didn't have an application that would allow him to do these calculations, especially efficiently. Because one could take some of the X++ applications that calculate those and use a karma approximation of no electron transport and do the calculation. However, this would be very inefficient, given that you will need to wait until the photons reach the scoring volume and then compute the energy deposition as the photons interact. And we know that this could be very inefficient, especially if it's a volume covering a small solid angle in space. So for that reason, a new EGS NRC application was developed called XKarma, explicitly developed for the calculation of karma in volumetric regions using a track length estimation. So it has 2 modes: linear track length, whereby when the photon crosses your scoring volume, you compute the karma using track length estimation. But you could use another mode, which is exponential track length estimation, where it will be very useful if you have a lot of material between your source and the scoring volume, and there's not many photons reaching the scoring volume, for instance, in shielding calculations. And then you use this exponential track length estimation that will allow you to ray trace ray trace the path of the photon through the material and allow you to compute the contribution from this photon directly in the scoring volume. To compute KERMA here, you need databases of μen or μtr values that you can obtain using the G code yourself. And depending on whether you use μen or μtr, you'll be computing collision KERMA or total KERMA. And you can calculate KERMA in individual regions, geometrical regions, but also in the volume that would be the total of all these regions. You can also compute the spectrum, but only in one, in the total scoring volume. And this little application can be hundreds of times more efficient than any of the other applications that we had for calculating KERMA. Uses of this application could be in radiation protection, in for treatment plan system calculations, for the calculation of backscatter factors using in dosimetry protocols for X-rays, and also for shielding calculations. We also have an app for X-ray primary standards. We know that the primary standards for X-rays are air KERMA based, and the actual primary standard is a free air chamber. We have two at the NRC. We have a medium energy free air chamber and a low energy free air chamber. We developed in around 2008 an application that would allow us to calculate all the corrections that you need to link a charge measurement in the collecting volume of the free air chamber with the collision KERMA. All these corrections can be calculated using a self-consistent approach with the Aes Nrc Monte Carlo simulation code. Many groups do calculate their corrections using Monte Carlo techniques for free air chambers. However, there's one correction that still is measured, because it's the most important correction and can be up to 5% in very low energy X-ray beams. And the fear here is that with the significant uncertainties that there are in photon cross sections, that there could be large systematic uncertainties in calculated corrections. However, I have recently done extensive calculations of this attenuation correction for a large number of photon beams from 10 kilovolts up to 80 kilovolts for a large number of filtrations, and compare these calculated attenuation corrections with measured attenuation corrections. And I'm showing in this graph the comparison for the 50 kilovolt beam for different aluminum filtrations compared to the measured values. And we see that the agreement is better than 0.2%. So that's a very good agreement. And if you use thicknesses over 1 millimeter of aluminum, the agreement is excellent between the measured values and the calculated values. There's only a systematic 0.1% uncertainty for softer beams. So I would argue that we are getting close to being able to use Monte Carlo calculated attenuation corrections for free air chambers. And one very interesting result from these calculations is that regardless of whether you use the renormalized photoelectric cross sections or the standard XCOM cross sections, this attenuation correction is actually not very different. So it's irrelevant which one of the two you use. So this is all I wanted to say about reference air KERMA to air KERMA calculations using Aes Nrc. So now we're going to be moving to those calculations that we have in Aes Nrc. The two workhorses for those calculations in Aes Nrc are DOS XYZ NRC, that is very well known in the community of clinical physicists. They use it to compute for quality assurance when they're computing their dose profiles from their Linux. And then there's DOS-RZ NRC that allows you to do calculations in cylindrical asymmetric geometries. And then we also have the CAV-RZ code. It's tailored for the calculation of correction factor for ion chambers. But then with the inclusion of the X++ library in around 2005, we were able to model more sophisticated geometries, and we could model ion chambers in all their details, provided the information was available. So the very first C++ application that was developed for this purpose was Cavity. We're trying to prove that you could use a smaller code that will give you more all the features available in Aes Nrc. So Cavity can be used in dose calculation mode, so you can obtain the dose to an ion chamber cavity, and you can model all sorts of ion chambers. And in dose calculation mode, you can also request to obtain the electron fluence in that cavity. So you can also obtain this quantity. And there's another calculation mode for cavity where you can get the wall correction as well, as you could do with Aes Nrc. Then the X-chamber code followed then Cavity and was then developed to be able to do in phantom calculations very efficiently. So it was found that if you wanted to reproduce depth dose curves with experimental measured depth dose curves, you needed to include the ion chamber in your simulations. And if you wanted to do it for many depths, this could be a very time-consuming simulation. So very sophisticated variance reduction techniques were included in this code that would allow you to do the simulation on the fly in just one go at different positions of the chamber very efficiently. So, and this is the code per excellence that is used for calculation of KQ factors to obtain the calibration coefficient for Linux from a calibration coefficient for Cobalt 60. You can calculate all sorts of perturbation corrections and realistic depth dose curve and ionization profiles in Phantom. We recently did some simulations with X-chamber 2 years ago to assess the impact of the recommendations of the ICRU report 90 that recommended an update of the mean ionization energy for calculating the stopping powers of water. And we found that redoing the simulations for 3 different ion chambers, that there was not a significant impact on the KQ values that are available in TG51 for dosimetry in Phantom, dose to water dosimetry. So now, what can you do if you have a simulation and you want to verify that your calculations are correct or that there's no big mistakes? So one first step that you could do is compare with other EGS NRC applications. So if you're using EGS NRC and you create your own application, or you're using a simulation of something very complex, then you can try to use any of the other applications that compute similar quantities or the same quantity and just confirm that you're obtaining the same result. This is a very first step that you can do to verify your calculations. Ideally, you should also be able to perform experiments, but that's not always possible, or it could be very, very complicated. But that would be the ideal situation where you have a Monte Carlo simulation and experimental data to back up your results. Another possibility is to use a theoretical validation. So you could run those calculations under, for instance, ideal conditions called final conditions, where you know what the result is. And then when you run your simulation, you see if you can reproduce this expected value. Or you can also do calculations on the charged particle equilibrium, and you would expect your dose to equal Kerma. That's another way of verifying your calculations. And ultimately, also comparing with results obtained using other Monte Carlo codes is also a very good option that I encourage people when they collaborate to do. So obtain the same result with different codes to make sure that there are not major differences. So the take-home message is that any well-validated Monte Carlo simulation code is a very powerful tool that you can use in metrology to perform impossible experiments. So thank you so much for your time and your attention. I can take any questions.
I don't know whether the applause comes in, the audio. Thanks, Ernesto, for this introductory view on Aes Nrc. Like I mentioned in the beginning, the way this this web meeting works is that questions are addressed in the end. So I would ask anyone who has questions to be addressed to Ernesto to stay tuned, and maybe they can type them now if they want, but we will address them at the end of everybody else's talks. So I have a few myself, so should time allow, I would ask also some questions. So now in thanking...
I'm sharing the screen right now, right? Sorry.
Yes, take your time. So while Ernesto leaves his screen, I'm presenting the next speaker, who's Grichar Valdes Santurio. Grichar works as a medical physicist in a Danish hospital whose name I cannot pronounce. I would not dare to do, but he will. And Grichar has been a PhD student a few years ago, and he used one specific Aes Nrc code as part of his PhD thesis, after which he published a couple of papers. So he will be talking about one of the applications of the apps that Ernesto introduced. So with that, I welcome Grichar. Thank you for coming in. Please share your screen as soon as you're ready.
Can you see it?
Mm-hmm.
Can you see my screen?
Yep.
Okay.
You should go into presenters mode. That's great. Okay.
Perfect. So first of all, thanks a lot for inviting me. And then it's not that I will talk about the specific application. I will talk more about an AUSCAP object that I developed for what I have developed too for my PhD. So most of this presentation, it will be like results, as Massimo mentioned, of my PhD that I did a few years ago. And the name of the hospital is Halo Hospital, which stays up here. So the name of my presentation, or the title of my presentation, is Monte Carlo role in addressing ionization quenching effect for organic plastic scintillators in MV dosimetry. So as an overview, I will briefly take a little introduction motivation, then talk a little bit about scintillator dosimetry. Then, of course, Monte Carlo. So these are the two AUSCAP objects that I developed, cumulative absorbed dose and light yield scoring. Then I will finally address the ionization quenching role in MV photon dosimetry, like quantifying it. And then I will just say a little conclusion and take home messages. So as I see it in radiotherapy, or not more as I see it, but as it is stated in the course of practice, the TRS 483, which was recently published like a couple of years ago for small field dosimetry, and the TRS 398, the dosimetry can be divided into three. So I see it as absolute dosimetry, in which it relates you relate the absorbed dose to a point in water for a quality Q, typically it's cobalt, with the detector reading through the calibration coefficient. Then you take that calibration coefficient to estimate on the clinical conditions in a reference conditions for reference field size. So you relate that to the absorbed dose in order to estimate the absorbed dose to a point in water. And then you have, as Ernesto mentioned earlier, you need to have a correction factor that takes from quality Q to quality Q0. Typically, it's like, as I said before, cobalt. And then you have relative dosimetry, in which is just whatever is outside reference conditions. Typically, you just multiply to estimate that absorbed dose to a point in water for the small field or whatever field. You multiply by whatever is estimated for the reference field size or machine-specific reference field size with the output factor. And this output factor has this shape as it has been defined in this small field protocol. So in this work, what was of our interest was these two correction factors, since my PhD was about small field dosimetry, so also we wanted to extrapolate it to KQs as well. And then we wanted to see how much was of the ionization quenching, among other effects, how much will that affect when you try to estimate these correction factors. Also, it is worth to mention that in this small field dosimetry protocol, they stated that the output correction factor was 1 for scintillators, but they didn't address the quenching effect. So that was a big part of my study. Yeah, so this is the main goal of that study that I did for my PhD. So first of all, why fiber-coupled organic plastic scintillators are so appealing for dosimetry? So it can be built in a rather small sensitive volume, less than 0.01 cc. As you can see here, I don't know if you can see there is a green spot here, so that symbolizes the sensitive volume of the scintillator, and this is attached to the optical fiber that goes to the photomultipliers and so on. Then it has a high degree of water equivalence. For example, this paper by Bedar, I think in the early 90s, shows that for different energies, the scintillator, which is the round dots, is almost behaves almost like water. Then it is perturbation-free, or many people have claimed that it's perturbation-free. So this is the TRS 483, and we can see here, as I mentioned earlier, that this output correction factor for the plastic scintillator is 1, of course, without addressing the ionization quenching effect. So, in our opinion, all dosimetric models are they have this shape in which is just divided in 3 main fields: the energy absorption, the signal production, and the signal detection. So if we see here, we compare, for example, ionization chambers, which they have been the backbone of radiotherapy, with organic plastic scintillators, like each of them, they have like good qualities and bad qualities, as you know, life. So for any absorption, we can see that for the ionization chamber, for example, the absorbed dose to water is not exactly equal to the absorbed dose to the sensitive volume. It has perturbations, the stopping power ratio from air to water. The detector size doesn't behave as a point in water, and we need to remember that it's absorbed dose to a point in water is how it is stated in the protocols that it should be. We have pressure and temperature. Now, in the signal production, we have the W, the average energy needed for producing a per electron ion. So this one is rather flat, and it kind of doesn't depend of energy. So this is a good quality. And now it has recombination losses and leakage. Like typically all of this is well characterized under certain conditions, of course. And then organic plastic scintillators is almost, since they are super almost water equivalent, it's almost like measuring directly those to a point in water. And they have the ionization quenching effect, which hasn't been quantified for photon fields. And they have some temperature dependence. They have stem signal, fiber degradation, signal to noise ratio, and so on, which is not as good as the ionization chamber, but it's pretty decent. So the way that we can see the ionization quenching is as we see the W here in the signal production for the ionization chambers. But again, this needs to be quantified to see how much of an effect, or how much will that affect later on. Of course, as I mentioned earlier, we have also pitfalls for the scintillator. One of them is the stem signal created in the optical fiber. There's many ways of removing it. One of them is the chromatic removal. This is basically a Cherenkov that goes through the optical fiber. So in this paper, they presented several methods, and then they show how efficient is the chromatic removal. So you can remove it, it's perfectly fine. Then you have the temperature dependence. Again, in this paper, they show like a linear formula that you can just use it and take into account, super efficient, everything fine. But then there was a problem again with the ionization quenching. So the ionization quenching was first described by Burks in the 50s, in which it relates the light per length unit with the scintillator efficiency, which is this A here, times the ionization density or stopping power over 1 plus the KB, which is the ionization quenching parameter. Is called that way. It has a long story, but that is called that way. You can't actually separate those two, times the stopping power. And if you see that this was proposed as it was found that there was no linearity between the light yield recorded in the scintillator and the absorbed dose or the absorbed energy. So if you can see for low energies, the relative light yield has like this shape, and then it kind of stabilizes when it's more than 100 keV, and that's basically because it depends on the stopping power, as we will see that it goes down. So it has a really sharp shape below 100 keV. So therefore, that contribute to this non-linearity effect. Then in 2016, Sam Bedar and Luc Villieu, they did a review of this formula. So of course, the most appealing way of seeing is dividing the first formula or the stopping power, and then you just integrate over energies, and then you get this beauty here, in which they replace the stopping power for the restricted stopping power, and then they integrate over all energies. But in this one, it's assumed that the charged particles will just fully be stopped in the cavity. And then in this, later on, for my PhD in this paper that I published, I proposed this formula here for taking into account the quenching of all possible secondaries created and so on. So it's just modified, and it's just kind of the same formula, but I integrate from the maximum energy in which the charged particle entered the scintillator down to its minimum energy, or if it is absorbed, then zero, and then I did the sum. Of course, this formula just screams Monte Carlo. This is so appealing for Monte Carlo to be computed to be used for computing this this light yield, as it uses of course the restricted stopping powers, but also it uses the full spectrum of charged particles that is in that cavity, and then to fold them, the best thing to do is to do it through Monte Carlo. So, and that's exactly what we did. So we went and grabbed a whole Monte Carlo. We used Aes Nrc, and for determine. So we wanted to determine the absorbed dose, of course, and then the light yield. Now, why Aes Nrc? Basically because it's an open code. So if you go to this link, you can see how the code is written. You can modify it as you please, and then you just compile and go on. It's extremely efficient. It has C++ libraries, and as Ernesto mentioned, you can just simulate really complex geometries and so on, and yeah, many other things. So I was really interested in computing the cumulative absorbed dose in my scintillator, since as I mentioned before, the region of interest was low energy electrons, and then I wanted to see which part of those energy electrons contributed to the full, as when I integrate the full spectrum. So for that, I developed this Ausgab object based on an existing one, which is Aes dose scoring. And then I just basically, what it does is just integrates the spectrum until a certain energy, a certain cutoff energy that you define, and then you do it for all energies that you want to, and the full spectrum, and then you can see which fraction of the absorbed dose of those low energy electrons contribute to the full integration. The way that is defined as an input is like this, in which is you just put this code or this piece of code in the Ausgab object part of the C++ codes. And the good thing about having an Ausgab object is like it doesn't depend on the application that you're using. So you can use it in whatever C++ application. So you can just actually take out as many info as you want. So this is how it's defined. You need to define all of these parameters, and this is the one that is added, which is this kind of energy that you want to integrate to. And this is how it looks, the output, the same as Aes dose scoring. And this is the value that you're after with its uncertainty. So then, for solving, as I mentioned before, this equation that was really, I think Monte Carlo can really take good care of this. I developed the Aes light scoring also as an Ausgab object, and it's defined in the same kind of way, in which the only thing that you need to define now is the KB in the equation up here. And then of course you don't need to define the A, because we just want to do relative measurements. So of course, then when you divide this value over the same for a different spectrum, then the A it depends on the same, it will be from the same scintillator, so it will cancel out. But you know, you can always put 1 if you want to. And then this is how the output looks like, and it's the same kind of shape. And then you will get down here the light yield, and then you will get its uncertainty. And of course, as Ernesto mentioned before, whatever thing you do, you need to validate it. So I validate this Monte Carlo Ausgab object that I did with against an analog method. And then here you can see the one in blue is the one that I did, and then the analog method is the black line, which is kind of really hard to see. And then in this part of the axis, we can see the relative discrepancies between them. Of course, I did this because it's really hard to solve that equation in analog method. So I did this like in a rather simple condition. So then it was easy to do, so to say. And then you can see that all the relative discrepancies are less than 0.5%. But the lowest energy one, which was less than 0.9%. So it's also, we consider that was a good agreement. And then I also validated against some published experimental values in this paper here, Froland et al. From 2008. And then you can see that it has a really good agreement, and these dashed lines are the uncertainty of the experimental values. So it has a really good agreement, but the lowest energy, and you know, in that paper, actually they claim that they have some sort of uncertainties and some sort of errors in their electronics. So for these lower energies, they kind of didn't trust the data. But even though that they publish it, and it's really nice that they point that out. So our EES light scoring was fully validated. So we were really happy about that. So again, coming back to what we wanted, so we need to see how much the ionization quenching affect the beam quality correction factor, the KQ, and the output correction factor. So for that, we came up, as you see down here with this, in this paper, I came up with this factor, like ionization quenching correction factor, in which you can quantify how much you're losing in absorbed dose just because of ionization quenching, in which it will be the light yield when there is no ionization quenching, or the light yield when there is ionization quenching for that quality Q. And this, of course, can just be, it's only possible with Monte Carlo because you will always have ionization quenching in scintillators. And we propose that for determining these values, you need to multiply by this K IOC. So for doing that, we also did experimental measurements for digesting this. We measure output factors experimentally. So we have the fixed energy of 6 MV, and then we have these small field sizes, and then we have the 10 by 10, which is the typical reference fields in normal clinics. And then we have also these different beams in which the jump of energy is bigger. So you have bigger spectral differences compared to the first situation. And in this one, we compute, or we measure the KQQ. This is how our experimental setup looks like. So this is our rig. This is a variant true beam, as you may see. The detector is just hanging down here, and then we come from underneath with the water tank, and the whole positioning system is based on this optical methods, with these optical telescopes. So we have a precision of less than 30 microns. So we have a really good reproducibility. So once we compute the cumulative absorbed dose, we can see here the results. Is the normalized cumulative absorbed dose for all of these field sizes, or the electron or the charged particle energy in the cavity. So we can see that here for electrons lower than, or electron energy lower than 100 keV, we have like a small difference between the 10 by 10 and small fields and the rest of the small field sizes. And here, for when you have difference of energy from cobalt to 15 MV, you see that for 100 keV, the jump is just huge. So just based on this part of the study, we would expect that the ionization quenching will be extremely more relevant, or will influence more when you have the KQ situation than when you have like a different small different field sizes with the same energy. So this ratio that I mentioned earlier, the ionization quenching correction factor, we computed it for the two scenarios as I mentioned before. And then we can see here that for small field sizes, like the spread difference will just affecting 0.6%. So you can say that it is almost negligible. But however, if you consider from 4 MV to 15 MV, the jump is like 4 times more. So it's 2.11% that you will get of difference between these two. Therefore, we will expect that the KQ, the beam quality correction factor, if you want to measure it with a scintillator, then because of ionization quenching, you will get like a different shape. Now physically measure the output factors, and then we compare them with the Monte Carlo that we compute without the ionization quenching and with the ionization quenching. So here you can see the experimental measurements, and this is the pattern just represents the uncertainty of the experiment, and this is the relative discrepancies between them, and we can see that all the points just fall within the uncertainties of the experiment, and the relative discrepancies between them is less than 1%. So that's basically why in the protocol wasn't taken into account, because all the published data that didn't take into account didn't really observe this effect because it's really a small effect. However, when it comes to the beam quality correction factor, here we can see it's the same sort of plot in which we will have experimental measurements and the uncertainty of the experiment. And then the red dots are without the quenching effect. We can see that it's kind of a flat line if you would like to fit it. So it's almost kind of constant, or regardless the energy. But however, the Monte Carlo with the KB, so with the ionization quenching, follows experimental measurements. And the uncertainty between them is less than 0.5%. So it indicates that the ionization quenching plays a big role in the beam, if you were to compute the beam quality correction factor using plastic scintillators. So the conclusion of that study is again the ionization quenching affects 0.6 plus minus 0.2% from a field size of 0.5 times 0.5 and the reference of 10 by 10, and 2 plus minus 0.4% when computing the beam quality correction factor using 6 MV as a reference beam quality. And because of that, an energy dependence of the scintillator was found because of ionization quenching. Now the take-home message or messages is that the ionization quenching effect can be indeed quantified for fiber copper organic scintillators using Monte Carlo techniques. Monte Carlo is a powerful tool which allows to explain processes that otherwise are extremely hard or almost impossible to describe. And for all Monte Carlo simulations, a thorough validation is actually needed. And I want to say goodbye showing this picture, in which this picture was taken from my PhD office, in which, you know, if you look at the right window, you see that it's a little bit, the sky is a little bit gray. It's not as nice as at the left. So with this, this say to me that even though we can look at the same thing, we can have different visions of it, and then we need to really, there is no absolute right or absolute wrong, so we need to respect each other's opinion and point of views. Obrigado.
Obrigadissimo. Grichar, thanks for keeping time. Also, you were just slightly out of time, but we will have a little bit extra time in the end because the next session is not as long as ours. But keeping in mind that we have the questions and answers session at the very end, with this, in thanking you, I want to now switch to another code. As Ernesto mentioned, there are several codes that exist in radiation dosimetry that have been applied over the past several years. And in this session, we explore Aes Nrc and the Penelope. And the next two codes are focusing on applications of the Penelope code. So the first speaker is Jorge Borbinha. He's speaking from Lisboa. And I just passed you the screen, George, so you can introduce your institute, because I wouldn't want to make mistakes. I forgot now what's your affiliation, so please speak it for yourself. Thank you, George. George, you have 20 minutes like the others.
Okay, thank you. Good afternoon, everyone. My name is Jorge Borbinha. I am from Instituto Superior Técnico, which is part of the Universidade de Lisboa in Portugal. And I will be here speaking about the work I am conducting during my PhD, which is entitled Radiation Dosimetry and Radiobiological Effectiveness Issues in Personalized Targeted Radionuclide Therapy. So it is about radionuclide dosimetry using the Monte Carlo code Penelope. So, according to the World Health Organization, cancer has caused more than 10 million deaths worldwide in 2018, and WHO predicts this number will grow to almost 40 million in 2040. Additionally, more than 60% of cancer patients can benefit from radiation therapy at some point in the management of their disease. And so it's time to go to a present day problem that is independent from the treatment modality employed that influences cancer treatment, which is the heterogeneity that is present in tumor tissues. Tumors often display different types of heterogeneity at the time of treatment, which can often be overlooked by professionals during treatment planning. Over the past decade, a significant amount of attention has been given to the use of functional and anatomical imaging, such as PET-CT, and contemplates parameters such as radiation attenuation, metabolic activity, oxygen supply, etc., in order to identify the phenotypes inside the tumor mass. A tumor phenotype is a subvolume inside a tumor that is composed by cells that have different phenotypic and genetic characteristics than cells in other subvolumes of the tumor. In figure 1, you can see a tumor from a PET-CT image that has been divided in 4 different phenotypes. And something that is important here is that not all the phenotypes in the same tumor mass exhibit the same resistance or sensitivity to the same treatment. And so the way to move forward here is to develop a therapy directed to the tumor phenotype. Targeted radionuclide therapy, or TRT, is a cancer treatment modality that uses a targeting molecule which is labeled with a radionuclide and is able to deliver damaging ionizing radiation to tumors. When compared to external radiotherapy modalities, TRT presents several advantages, such as a more localized tumor irradiation and tumor cell specificity. Moreover, in external radiation therapy, the concept of tumor heterogeneity has already been extensively addressed in the literature by concepts such as dose painting and escalating dose. But nevertheless, treatment techniques that consider tumor heterogeneity in targeted radionuclide therapy still require further investigation. So the main objective of this study was to ascertain if irradiating different phenotypes within the same tumor mass has a significant impact on the absorbed dose distribution in the tumor when compared to irradiating the tumor with only one radionuclide. Additionally, we intended to investigate the dosimetric effect of each decay mode of each radionuclide on the tumor tissue and on the healthy tissues, and also to try to ascertain the feasibility in terms of strategic dose delivery to the tumor phenotypes of a novel personalized targeted radionuclide therapy that is directed to the phenotypes. So we developed the tumor model, which was based on a tumor found in the bibliography, on images found in the bibliography. And it was divided in 4 clearly distinguishable phenotypes, which are numbered from 1 to 4. And it was placed inside the right lung of the ICRP adult reference female phantom, which is an average-sized phantom depicting the average woman in Europe. The phantom was developed by ICRP and the crew. You can see that the representation of the tumor in figure 4 inside the right lung. And on table 1, you can see that the characteristics for the 4 tumor phenotypes, they all have different masses and different mass densities, and they are composed by different materials, which means that they have different elemental compositions. So 2 main irradiation scenarios were considered in this study that are represented in figure 5. On the top of figure 5, the scenario 1 is represented, which is the current practice, on which all 4 tumor phenotypes are irradiated by 1 radionuclide. And the second scenario, which is represented on the bottom of figure 5, is the ideal scenario, in which each tumor phenotype is irradiated by a different radionuclide. So MC simulations were performed on the tumor model and on the voxel phantom using the PENEASY main program with the Penelope 2014 code package. And the S value, which is absorbed dose per cumulated activity, was calculated in the 4 tumor phenotypes and in some healthy tissues that are surrounding the tumor, such as right lung and breast. For each of the considered radionuclides. On total, we considered 5 radionuclides in this study. The decay mode information was accessed through the data files from ICRP publication 107. And then we had to decide which parameters we would use to evaluate the dosimetric efficacy of TRT directed to the tumor phenotype. The first parameter is the maximization of the S value to the tumor, which would maximize damage to tumor cells. The second parameter would be the minimization of S value to the healthy tissue, essentially in order to prevent reaching the toxicity levels for some radiosensitive organs, and also because literature has related those to healthy tissues from radiation therapy with secondary radio-induced tumors. And the third parameter we used was dosimetric efficiency, or DE, which is the ratio between S value to the tumor tissues and to the healthy tissues. And it was selected as the way to meet halfway between the other two parameters. Furthermore, a computational validation was performed in this study, because for a therapeutic application, the dose needs to be determined not only at the organ level, but also on a scale comparable with the range of emission of the particles. So the computational validation was performed in 2 steps. Specific absorbed fractions, or SAF, were calculated in the ICRP reference phantom, and S values were calculated in cellular models. The MC simulations were run using Penelope in the lungs of the ICRP reference phantom for monoenergetic beams of photons and electrons between 50 and 1000 keV, and we used cross-irradiation and self-irradiation configurations. And the results were then compared with the bibliography. The results from this validation are that the SAFs had a relative difference to the bibliography, under 1% for cross-irradiation and under 0.5% for self-irradiation. Regarding the cellular S values, they were also calculated using Penelope on a cellular model, essentially composed by 2 concentric cells, which are composed by water. And the inner cell had a 5 micrometer radius and represented the nucleus, and the outer cell had a 10 micrometer radius and represented the cytoplasm. And in these, we considered the emissions of 3 radionuclides and compared with the results obtained by Falzone et al. The calculated S values had an average relative difference to bibliography under 0.0% for cross-irradiation and under 2.3% for self-irradiation. So therefore, we considered the computational validation was successfully performed in this work. Moving on to the results and discussion of the MC calculations considering the tumor model and the voxel phantom, we performed the calculations and determined the optimal tumor configurations. This is the optimal radionuclide and the tumor phenotype pairings and the respective effectiveness. And then we try to investigate the possible effects that a non-homogeneous absorbed dose distribution in the tumor can have on the outcome of cancer treatment. The statistical uncertainty of this calculation was always under 0.5% for tumor tissues and 1.5% for healthy tissues and dosimetric efficiency. As you can see, figure 7 shows the S value for the tumor tissues and the healthy tissues in the right y-axis, and on the left y-axis, and on the right y-axis, the dosimetric efficiency is presented for all the radionuclide combinations considered in scenario 1 and in scenario 2. Looking at the graphic, we can see that the highest dosimetric efficiency is achieved by iodine 125. Iodine also minimizes the dose to the healthy tissues, and terbium 161 is the configuration that is able to maximize the dose to the tumor tissues. And by looking at the combinations present here, we can see that irradiating with a mix of radionuclides can improve dose to the whole tumor mass. For example, looking at the configuration C1, which uses iodine on 3 phenotypes and terbium on 1 phenotype, the S value to the tumor of combination 1 increases by a factor of approximately 2.7 with respect to using only iodine 125. The S value bar for the tumor tissues is higher than using only iodine. And if we look at combination 2, on which terbium is used on 2 phenotypes and gallium is used on the other 2, we can see that the S value to the tumor of the combination 2 is approximately 3.6 times higher than using only gallium 67. On this slide, we can see an analysis of the dose distribution using only terbium 161, which is the configuration with highest dose to tumor. In figure 8, we can see the S value for all the 4 phenotypes and for the healthy tissues and the dosimetric efficiency for each of the considered radionuclide decay modes. And on this graph, we can see that the highest dose to tumor is, as expected, achieved by beta electrons, which are very energetic, and is about 1 order of magnitude above the other decays. The X-ray and gamma photons also contribute with a pretty significant amount of absorbed dose to the tumor tissues, approximately similar to the one of Auger electrons. And we can also see that beta electrons and gamma photons, which are the highest, which are the decay modes with the highest energy, also depict very high dose values for the healthy tissues. The Monte Carlo statistical uncertainty for this case was always very low for the tumor and fairly low also for the healthy tissues. Additionally, we performed an uncertainty analysis in which we analyzed the possible source of uncertainty that could influence the MC simulations presented in this work, and also the eventual possible application of this technique in a clinical setting. So the first source of uncertainty is the uncertainty present on the decay schemes of the radionuclides, of the energies and of the yields considered, which was at least 20% according to the bibliography. The statistical uncertainty from the Penelope simulation was presented in other slides and was fairly low. Furthermore, the uncertainty of the Penelope cross sections is strongly dependent on the energy of the particle, but it is under 2% for particles above 1 keV, and mostly under 20% for particles between 1 keV and 500 electron volt. The uncertainty of material compositions in the simulations was consulted in ECRU report 44 and is mostly under 5 to 10% for photons and electrons. The uncertainty of using an average size reference phantom as opposed to a patient-specific phantom, which would be a more accurate representation of an individual patient anatomy, is mostly under 25% according to the bibliography. And we also wanted to estimate the uncertainty of the activity that is administered to the patient. According to the European Association of Nuclear Medicine, this uncertainty is 94%, because during, for example, a lutetium treatment for radioendocrine tumors, the dose to the tumor can vary between 10 and 340 gray. So, moving on to the conclusions of the study. The results from the simulations using Penelope clearly show that irradiating the phenotypes in the tumor with different radionuclides can enhance the dose in the tumor and minimize the dose to surrounding healthy tissues. Relating to the expected implications for patient care, the use of this technique can help with dose enhancement in each tumor phenotype, which may increase therapy efficacy and success rate, and at the same time contribute to minimize damage to the healthy tissues, because the necessary exposure to ionizing radiation can translate it into harsh dose effects to the human health. And therefore, this work contributes to the evolution of the field of personalized medicine and precision medicine. Moving on to the future work, it is predicted, on the continuation of my PhD thesis, to perform the acquisition and segmentation of clinical, anatomical, and functional imaging, such as PET-CT, that depict tumors that are distinguishable in phenotypes, and then implement these on the Penelope MC code and try to investigate to further investigate the uncertainty of using a reference average sized voxel phantom and of using a voxel phantom that accurately describes the patient of the individual anatomy of a patient. Furthermore, we intend to assess the biological effectiveness, also using Monte Carlo codes, in the tumor phenotype and in the healthy tissues, because for therapy applications, it's very important to understand what is the biological damage for a given radiation dose. And we also intend to design a dosimetric formalism that could be able to correlate macro and micro and nano dosimetry, mainly in the scope of trying to make a more accurate assessment of the effect that a nominal dose to the tumor tissues could have on the outcome of cancer treatment. Thank you for your attention.
Okay, sorry, I could not hit my unmute button. Thank you, George, for this, let's say, preclinical or maybe pre-animal study work that you did. Congratulations. So while we leave the questions for the end, and we are perfectly on time. We are really exact on time. And I also want to take the opportunity to thank the participants, because we did not lose many in this very Monte Carlo specific session. We started with 83. We have a mortality rate of 5/83, so that's pretty good. Thanks for keeping tight. So I want to pass the word and the screen to the next speaker, is Pedro Teles. He used to be working in the same institute with George in Lisboa, and Pedro moved recently to the University of Porto in the north of Portugal. So Pedro, please turn on your microphone and share your screen, and you have 20 minutes.
Okay, hello. Oh, okay. Sorry. First of all, I'd like to thank Massimo and the Brazilian Metrology Society for this opportunity to present some of the work that we performed about a year ago in the framework of, when I say we, it's me and George, who is also here with us, in the framework of a project in which Massimo also participated. In fact, he was the coordinator. So I think there was already an introduction more or less about this, but I think I can also talk about it a little bit. So in terms of the importance of the calibration of radiotherapy beams. So I think everyone agrees here that you need to know the dose, the prescribed dose, to a very high accuracy. Here I mentioned this 5% because it's the value that is in this report from ICRU, but it's probably better to even achieve a lower accuracy. So there was a need for a common code of practice, which is this technical report by the IAEA that I think most people, perhaps in the audience, know about, that provides a common code of practice for the calibration of linear accelerators in hospitals. So like I explained, so this dosimetric system is common for, I think, all types of radiotherapy modalities. So it provides these NDW, which are the calibration factors for dose to water for the different types of dosimeters. Okay. So there's the problem of karma to absorb dose to water. So most primary standard laboratories use air karma determined using a cobalt source. But what you measure in the hospital is dose to water. So you need to have some kind of factors to transform one to the other. Okay, so here I show some of the variations that you can see in these two calibration factors for different ionization chambers. You can see that the variation is a bit high. Also, you can find some variation even using the same ionization chamber on the order of 0.8%. So the formalism that is used mostly by TRS 398 is this formalism here. So the dose to water is determined using the measurement that is made using a specific ionization chamber and in the conditions specified by TRS 398 and in a specific LINAC. You have a calibration factor that is provided by a standards laboratory, but you also need first to correct for the quality of the beam. So you have to have this correction factor here that is usually called the KQ factor that transforms from the quality of the beam that you are measuring. So imagine that you are measuring a LINAC of 20 MeV photons. So you need to correct this for the fact that the calibration laboratory used a cobalt 60 source. And then you have other factors here that I'm not really going to talk about. I only wanted to stress the importance of these KQ values. So these KQ values can be determined using this fairly simple equation. So it's basically the ratio between the dose to water to the dose to air for the quality that is of the LINAC to the ratio of the dose to water to the dose of air to Q0, which is mostly cobalt 60. This is tabled in TRS 398 for most ionization chambers, for most beam qualities. So for instance, you have an example here. The beam quality usually is measured in terms of tissue to phantom ratio. And you can see the curves that usually have this kind of appearance for the different type of qualities and ionization chambers. So you can kind of know the value that you need by knowing this relation. So this tissue to phantom ratio is determined using the formalism that is also defined in TRS 398, or it can also be obtained from the percentage depth dose using the following expression, which was obtained from measurements performed in 700 different accelerators. So it's basically just a function that can transform PDD to TPR. Basically, recently the agency has decided to update this protocol for many reasons. I point some here in this slide, but mostly because in the past 20 years, so this document is from the year 2000. There have been many improvements, not only in the state of the art in the formalism for the determination of those correction factors, but also in terms of the computing power that you can use to make calculations using Monte Carlo. In this framework, we have started. This project here, called RT-Norm, was funded by Euramet in the framework of the Ampere. The Ampere, which is like a call for projects, and this project was financed to provide data for the updating of this document. So the participants are all pointed there, and also what the work packages that were part of the project were. At the time, I was also working at IST with George, and we were both working in this project, and we used Penelope to perform our calculations. Some of these were also published. So if you want to, you can also go to these papers that I mentioned here. It's not only these two, but there are others. But maybe in these two, you can find some information that is in more detail than what I'm saying here. We were the only ones that were using Penelope. Most other participants were using the EGS code. We performed the calculations using the PenEasy package, which is compatible with Penelope 2014. Some of the material files had to be adapted to be in accordance with the new ICRU 90 cross sections for air, water, and graphite. And we modeled the chamber geometries using the specifications of the manufacturers, but also previous works by other authors, not only from the project of RT-Norm, including Maria Pimpinello, which is a co-worker of Massimo, but also other works from Eraso. Sorry. The first thing actually we did was because we wanted to try to use the MCMP code to make these calculations. And in fact, what we noticed is that the MCMP code had not been tested for what is normally called the Fano test. So the Fano test is usually performed to test the consistency of the Fano theory, which states that the fluence of particles, of charged particles, should be independent from density. And so you can devise a kind of a formalism that can be easily simulated using the codes. We used a formalism that was developed by Saint Pau from the University of Barcelona. So we have to determine this Q value following the ideas that the density of the material in the cavity is the same as the material of the wall. And so we have this formalism, and so this value of Q must be always equal to 1. And what we observe here is that for lower temperatures, this value of Q in the case of MCNP is not close to 1 at all. So our conclusion, at least in preliminary terms, was that this code did not pass the test, and therefore it cannot be used to perform these calculations. After this, we started using Penelope. And so we simulated 2 different chambers, the NE2571 and the Exrodin A12S, with the specifications that are given here in this table. Here below you can see a plot or a graph showing the appearance of these chambers that were, as you can see, simulated with extremely high detail in order to obtain good results. Okay. So here I give some more specifications. Okay, so you have to be very careful with some of the choices you make. So for the KQ calculations, we used an SSD of 100 centimeters which is the one that is recommended in the protocol. But we had to adapt this for the cobalt-60 phase space files because they were measured somewhat differently. And we used, basically we tried to adapt the simulation to be as close to the specifications in the TRS document. In fact, we didn't determine the TPR directly. We used the approximation that I mentioned earlier. So we determined the PDD at 20 centimeters and the PDD at 10 centimeters, and applied this formula. And so we determined the energy deposition in the active volume of the chambers. We used different phase space files. Okay, so for those who are not familiar with this, so a phase space file is a file that records the particle fluence at a specific point, usually at the beginning of the production of the source, and it's measured usually at an actual linac. So you're actually simulating the actual fluence that is coming out of the linac source, and this is important to obtain good results. So we use this 6 values for the Varian chamber, and the 1 for the Electa, and also 1 for the cobalt-60 source that was taken from the IAEA database. We also used variance reduction techniques because otherwise it would have taken a really long time to obtain actual results. So simple particle splitting was implemented in the sensitive volume with a factor of 10. We also used a splitting factor for the phase space files, which is equal to 10 for the Varian beams and 200 for the cobalt-60 beam. This was done after a series of trial and error tests that actually took some while and were performed in order to try to improve the efficiency of the simulation without biasing the results. We also, since Penelope cannot be run in parallel, what we did was we ran several codes at the same time with different seeds, and afterwards we propagated the error, and this also allowed us to have a smaller statistical uncertainty in a faster in a faster way. Okay, so these were the results that we obtained. Here on the left side, only the ones that were determined by us, and here on the right side, in comparison with what was obtained from our partners at STUC, and also from the TRS 300, the data from the TRS 398 itself. Usually these are the way, I have already shown this, so this is usually the way that the KQ values are shown as a function of the TPR 2010. So in conclusion, the TRS 398 needs an update to conform with the state of the art. In terms of Monte Carlo simulations, the Penelope codes is very appropriate to perform these calculations. They were accurately performed by us in the framework of the RT-Norm projects, and we also submitted our results to the IAEA to be included in the next report. And that's it. Thank you very much. Obrigado.
Thank you, Pedro. Also for keeping time, keeping everything in time. So it's 20 minutes to 6 p.m. in Central Europe. So we have to the end of this session, we have just about 20 minutes. Now, I know that the next session will allow us more time in principle, but I also know that some of you cannot stay, some of you speakers cannot stay for much longer. So I think I will try and keep everything in the next 20 minutes or so, which we should be able to do, so that then you can be free. there's been a few questions that have been addressed on the Q&A window that most of you, or probably all of you, can see as participants. And some of them have been already answered, and they pertain to specific aspects on where to find some documentation from EGS. And these questions were addressed to Ernesto. And then there's a few open questions that we'll be reading in a moment. One point that I really would not want to leave without, so before we read all the questions that arrived, I wanted to ask Ernesto if you could indicate where can interested students or non-students, research scientists, can obtain training in EGS, something you did not mention in your talk. So how can they obtain sources of training, either by attending in person when the COVID-19 will allow, or online?
We have been actually thinking about starting next year to offer virtual courses. So we still don't have clarity of how we're going to do this, but certainly we are thinking of ways to adapt to this new situation. And so we've been discussing that. Right. So as of right now, there's no courses planned because of the current situation. But as soon as we have a plan, we're gonna post it probably on the GitHub distribution site, and probably try to make people aware of this possibility. Because I think that this will open the possibility to having more students take the course. Now, while we offer this course, I would point out there is a small document on the GitHub distribution site for Aes Nrc that has a getting started document that our colleague Reed created, where he made use of many of the labs that we use in our usual courses, so that people interested could start from zero knowledge and start building up their knowledge on how to use the system. So there is a getting started document in the documentation on GitHub. And the way you get to the GitHub page for Aes Nrc, you just type on Google Aes Nrc or Aes Nrc GitHub, and then you'll get the link to the repository. And from there, you should be able to access all the documentation. And by the way, the PDF for the G application is there now. My colleague, Frederick, was able to update the website to have the PDF there.
Okay, and this actually takes us to Ernesto, to one of the questions that were addressed to you from Mateus Rebelo do Nascimento. One of the questions was whether the G-code documentation is already available, and you mentioned that. Thank you. He has Mateus has another question on this new idea of obtaining X-ray spectra measuring the EGS PhD application. I was not aware of this name. If there is any new documentation about this topic on the webpage, what you can say about this.
So first, I think there has been a misunderstanding. This application, EGS PhD, is actually pulse high distribution calculation. So you were not going to get the initial fluence, like as in you get an X-ray tube and you get the spectrum. So the pulse high distribution code will compute the pulse high distribution in a material. So you can model a scintillation detector or something, and you can get the pulse high distribution. So it depends on what you're interested in. I'm not sure, but I think that this XPHD code is not available right now, but I think we can provide it if you're interested. But I'm not completely certain of that, so I have to check. So it depends of you really, what are you interested in? Are you interested in a pulse high distribution or the fluence coming out of an X-ray tube? So it will depend on that. And if there's interest in this XPHD code, we can certainly get in touch and make it available to you.
I think it would be great if this application will allow you to simulate an entire PhD, and so you obtain a PhD at the end of the code.
Exactly.
Okay. Now, there was a question also from Denison de Souza to George. This question is about an uncertainty that was quoted in the decay schemes of the radionuclides. And this appears to be, judging from Denison's question, to be higher than 20%. And that looks a little bit too high in Denison's opinion. George, can you comment on that? Is it too high or is it correct?
Yes, actually I had great difficulty researching the uncertainty of the databases for the radionuclide decay data. And so that 20% comes from an article which is Cassette et al. From the Metrologia Journal, issue 52, in which I am citing, in the radionuclide metrology community, it is generally admitted that after a good measurement with a serious evaluation of the uncertainty budget, the relative uncertainty of the uncertainty can be considered to be about 20%. It's what they say here. And this was also promoted by Muller, which was a former director of the ionizing radiation division at BIPM. And because I couldn't find a precise value for the uncertainty, I went and put in this value from this paper, which is in the bibliography of my presentation.
Which I assume Guilherme and the organizers are going to be made available as a recording or as slides. I assume so. Hopefully, yes. I don't. Yes. Yeah. Okay. That's great. So whoever wants to go and go back into the literature from George can go back into his presentation and take a look at that.
I can also type here the answer in the chat. I think I can.
Yeah, if you could, just in case anyone is interested, right?
That as well. Okay.
Now, going through, thanks, George, thanks. So going by the list of questions, there was also a comment that was made by the organizer of this meeting from Guilherme. And he was mentioning that Guilherme is organizing a master's course in radiation dosimetry, and is interested in organizing a postgraduate lecture about Monte Carlo code. So using a virtual platform, sometimes during the doctoral studies and master studies in Brazil, sometimes in 2021. So one interesting, I understand that maybe from Guilherme that one possibility would be to hopefully you being still involved in this event, which may be a sort of a one in a course of studies, not on a regular basis, but like during the doctoral masters and PhD studies. And so I understand Guilherme would like to invite you to be involved in this event in the future, should you be interested. But I guess this is probably something that we could discuss at a later date. So I wouldn't want now you to make a commitment to something which is not clear yet. But just to mention, there is this interesting opportunity to speak in a virtual platform for this PhD and master's course that is organized in Brazil by Guilherme. Now, there is a question again from Denison de Souza Santos. This time is for Pedro Teles, and this is about what happens for high energy beings. Denison writes, there will be a production of neutrons. Can those affect the calculations with Penelope? Pedro, do you want to answer that?
Yes, yes, I can answer. Well, there is no, Penelope does not follow the neutrons. So Penelope only simulates electrons and photons. So you cannot have any idea of what the neutron spectrum is from Penelope. You can use another code, so I think this has been done. I've read some papers about that. This can increase, the neutron production can increase quite steeply after a certain amount of energy. But with Penelope, you don't have to worry about the neutrons. That's my answer.
Although the questions was to you, I was just wondering whether Ernesto, although I know that AGS is not focused on neutrons, whether you want to add anything to this question.
Well, I think that if somebody wanted to account for the neutrons, the best way would be to use GM4 that has Penelope physics, and then you could also account for the neutrons. So that would be the way to go.
Now, I feel obliged to pay a tribute to Mcmp. I'm not a user of Mcmp, but I just wanted to add to what Pedro was mentioning before, that Mcmp failed the final test on a specific application of dosimetry that was of interest in a TRS 398, so a clinical dosimetry application. So I would not want those who are listening to think that Mcmp is just not a valid code. It depends on what you want to calculate. So you can still keep an open mind on what Mcmp can offer to you, even if it failed one of the applications from Pedro. One advantage of MCMP is that it has it can transport neutrons. That was the reason why it was invented.
What I wanted to say was that perhaps in terms of cavity theory calculations, MCMP is not well suited for that. But obviously MCMP, and I am a user of MCMP, and that's why I try to use it for this project, was precisely because I wanted to see if I could use it. But I think in terms of cavity theory, where you need to have the Fano theory working, you know. So obviously Fano theory also has some conditionals, and also cavity theory also has some conditionals. So in terms of cavity theory, perhaps MCMP is not well suited, but for everything else, especially for neutrons, is state of the art, obviously. So it's that's clear.
And I saw Ernesto, raising a hand. Ernesto, please.
So we published a study in 2015 where we compared Penelope, Gerand, MCMP, and Aes Nrc to find out how accurate it was in modeling small volumes of water spheres and seaweed, and compare them with single scattering simulations. And we find out that that MCMP wasn't able to converge to the right answer. And this is connected with the way the electron transport for this low energy is done. It uses a type 1 calculation with fixed steps. So because of the way the electron transport is designed in MCMP, it can be used for these accurate ion chamber simulations. So it's a limitation of the code, but yes, for any other type of calculations, it's a very good code.
So there was a question that is to all panelists, but before I get to that may take us eventually virtually forever, I would not want to touch on that question first. I also wanted to ask one question to Grichar, who hasn't been addressed any questions yet from the audience. And that pertains to what Grichar, what you showed in one of your graphs at the beginning of your talk. You were showing the, with the complementary trend of the quenching effect versus the production of light. So there was a slide in which you had this sort of one curve was going up and the other one was going down. So, and all of these problems of these plastic scintillation, organic scintillations that were conceived for high energies anyway, not for low energies, seem to fail, or in a way to behave in a way that is not ideal when you go down to lower energies. So one question that I had for you was, which I never thought of asking you before, even if we collaborated. So is that whether there's anything that could be done to reduce quenching by reducing the diameter of the probe. So if you made it even smaller, would that be working any better?
Well, I don't think so, because it breaks down to the spectrum. So it's whatever spectrum is seen. So you can have, I guess, like a rather small scintillator, and then again, it will depend on the spectrum that is seen. Because as you mentioned, you have this effect for low energies, like below 100 keV, mostly. And then, it doesn't matter which spectrum you're shooting with, you will always have that part of it. You can't neglect the first part of the spectrum. You can't neglect the high energy part of it, but not the lower part of it. So I don't think it will actually make any difference if you have smaller or bigger. In that concern.
Mm-hmm. Okay. Thank you. Thanks. So there was a comment and a question by Leonardo Pacifico. First, Leonardo, thanks you for all your presentations, and I pass the congratulations to you, of course. And then here's the bomb. Here's the question, and it's he'd like to ask, how is the uncertainty evaluation done in the simulation? And this is an entire session, if you want. And if there is any target confidence level, that's the easiest part. But I don't know whether any one of you wants to answer the uncertainty part. The question is open, wasn't addressed to any specific talk.
Yeah, what I would say is when we do these Monte Carlo codes, what they do is they just estimate the 1 sigma statistical uncertainty. So you're getting an average, and because of the random nature of your process, you get fluctuations, statistical fluctuations. So you evaluate the variance and then do an estimate for your statistical uncertainty at the 1 sigma level.
Now, I don't know whether Leonardo was alluded to type B uncertainties, which I was afraid of, but maybe I was wrong. So if we stay with the type A uncertainties for a moment, so the statistical uncertainties, there was something that was that Ernesto just mentioned a moment ago, was also linked to what Pedro was mentioning in his presentation, although he used a different code, but the principles are identical. Pedro, at some point you mentioned that to reduce your final uncertainty budget on your simulations, and given the fact that Penelope is a serial simulation, it's not a parallel, you can do a virtual parallel by splitting the job into n CPUs. So you run your simulations with different random seeds, and then you average the results together. So when you look at the individual runs that are run, again, sorry for the pun, run again with different seeds, do you see major differences between the results you get given a specific choice of random seeds?
You will not. You will never see. You will never. This is basically a workaround for the fact that Penelope cannot run in parallel. So basically, you just make it's by using different random seeds. What you are doing is basically you are sort of creating 10 virtually parallel simulations. So you will never get a very different results from each other. You're trying basically to reduce the statistical uncertainty. It's the only purpose of that technique. You're not really doing anything more than that. So you cannot, the results will eventually always converge to a very close value. It's impossible that they wouldn't. Otherwise, physics would be all wrong, I guess.
Otherwise, you would not be sampling a random number. Otherwise, Ernesto was moving his head. Yeah, so you.
I guess it would depend. These 10 different calculations will have a number of histories, and each of them will have their own uncertainty. So you'll see more differences if you run a small number of histories. But if you run each of them millions of histories, then the variation won't be that large.
Now,
actually, what the Penelope developers propose. So if you talk to them and ask them how you can implement Penelope in parallel, what they will reply is that you do this. So you just use different random seeds and then propagate the error, because it's basically like running something in parallel if you think about it.
I used to do that by hand in Havana, go to different computers and run simulations like that.
How you do now? How you do in EGS? How is EGS addressing this, Ernesto?
Well, with X, you can pass parameters to the code that say this. So we have a script that will send several simulations automatically to a queuing system. So if you have a cluster, you can, using the queuing system, you can send the proper parameters to the queuing system and also to Aes Nrc. And Aes Nrc will do automatically what Pedro just described. You just split the thing and also use different random seeds. It's just, it's done automatically.
Or it's exactly the same process.
Yeah, so you can do it using a queuing system like a PBS, a Torque, or a Grid Engine. But also you can, if you have your own computer right now, you can just submit it to all the cores in your own machine. So you can do that on Windows and Linux as well.
So sorry, no, please.
Oh no, I was just gonna, I thought, was there the Penelope application that allowed automatic parallel job submissions?
I'm sure there is one from Josep Sempau, but I haven't tried it.
But at least from what I know, and I did the Penelope course many years ago, maybe 12 years ago, and we talked about that at the time. Maybe, well, if it was 12 years ago, maybe it's somewhat different, but I think we had this discussion with George. I had this discussion with George, and George was a bit skeptical of this idea at first. And then I think we actually did contact, I don't know if it was Sempau or someone else, and they told us that it was just the same thing because it's not.
If I may add something here, yes, there is an application called CloneEasy, which was developed by Josep Sempau, and it works with the PenEasy main program with Penelope. But at the time, I was having some issues running it because of the C++ libraries in the computer in particular that we were using, and so we just ended up doing this manually because it's essentially the same thing.
Now, given that you essentially, Pedro and Ernesto, you already mentioned that both codes are not really running anything in parallel, but it's a sort of virtual parallelization, because in a way, Monte Carlo codes are approaching the simulations in a serial fashion. I have an open question to the platform, and it's really the last one I have for you. Is there any application of present-day dosimetry problems in which this serial approach of Monte Carlo simulations could fail? For example, in very, very high intensity pulses in which the density of ionization is extremely high, with this sort of treating each track independently of one another, is it going to be, so are Monte Carlo simulations in a way failing the serialization of the process in a high intensity pulses?
Yeah, we had that discussion recently with Marco McEwen and Frederick. And yeah, that's something that we have never explored, but potentially in a situation like what you described, there could be some effects that we're missing by doing it independently, yes.
Is there any questions that within you want to address to one another that you haven't done so far? Because I know that some of you have to rush away at every time zone you are. So with that, I want to thank you, speakers. Thanks also to Guilherme to host this session. And I also want to thank all the 77 participants that survived the 2 hours of Monte Carlo code session. That's a great success. I thank you, each of you individually. Thanks very much. Guilherme, you want to say anything?
Yes, of course. I would like to give thanks for Jorge, Grichar, Pedro. Pedro looks like my parents also, Peixoto, and also, of course, Ernesto. And yes, and then I would like to give all the thanks for the Massimo that know how I works here, and I want to continue this studio with my students that make a lot of questions here, but we're planning to continue this study here in the 2021, and then I invite all of you in this discussion also, okay? Then I would like to give thanks for everyone, and to talk that this section will be also in the YouTube of the SBN channel, okay? And if you want to distribute or make sharing for everyone, it will be there, all right? Thank you very much for everyone. And now I will give the coordinates for another section. Thank you, Massimo. Thank you, Jorge. Thank you.
Bye, everyone.
Richard. Thank you, Pedro. And Ernesto.
Bye.
Bye.
Ciao.
Ciao.
Ciao, everyone.
Obrigado. Gracias.
Por nada.
En italiano, eu não sei. Gracias.
Bye.
Valeu, obrigadão. Dando continuidade ao nosso congresso, eu gostaria de avisar que nós vamos ter um tempo de 1 hora nesse intervalo agora, por conta que um dos participantes da mesa não pôde estar aqui nesse horário. Tá? Então, nós retornaremos a continuidade nesse canal às 15 horas. Ok? Tá, às 15 horas, que é 40, 50 minutos. E aí eu vou retornar e chamar o Marcos Navarro, o Marcel, para fazer a sua apresentação. Ok? Obrigado.